Hello everyone, welcome to my channel. In this lecture we will discuss about separation columns. So separation columns. Recovery of natural gas liquid NGL from natural gas is quite common in natural gas processing. The recovery is usually done to produce transportable gas which is free from heavier hydrocarbon which may condense in the pipeline. Sometimes we want free gas from heavier hydrocarbon because these light hydrocarbon sometimes condense in the pipeline and it can create problems. Uh, Sometimes we need the purification or recovery of natural gas because to meet a shale gas specification. Sometimes we need shale gas specification, so we are doing natural gas recovery process. Sometimes we need maximize liquid recovery. So in order to maximize liquid recovery, we usually recover natural gas liquid from natural gas when liquid products are more valuable than gas. So Aspen HYSYS can model a wide range of different column configuration. In this simulation, in NGL plant, natural gas liquid plant will be constructed, and this plant will consist of three columns. The first column will be de-methanizer, which will be upgraded and modeled as a reboiled absorber column, which is nothing but a reboiled absorber column. The second column will be the distillation column, and it will be the de-ethanizer. The third one will be the depropanizer. So this is natural gas plant. So the natural gas plant, this is the natural gas plant. Here you have three columns: de-methanizer, the second one is de-ethanizer, the third one is depropanizer. Here you can see this is speed number 1, this is speed number 2, and this is the external duty to the de-methanizer. This is the reboiler of the de-methanizer, this is the reboiler duty, and this is the top product of de-methanizer. The bottom product from the de-methanizer will pass through a pump and it will go to the de-ethanizer. De-ethanizer is column number 2 and it will operate at partial condenser. So we will obtain the vapor product, and this is the condenser energy, and this is the liquid distillate product. Now this is the reboiler of the de-ethanizer, and this is the reboiler duty. Now the bottom of the de-ethanizer will pass through a valve to reduce its pressure, and then it will enter to a depropanizer. The depropanizer, this is the top product of the depropanizer distillate, and this is the condenser energy of the depropanizer. This is the reboiler of the depropanizer, and this is the reboiler duty, and this is the condenser duty of depropanizer. So okay, there are two feed. So now this problem is taken from the Aspen HYSYS book. So first of all, I will open this Aspen HYSYS book. It's taken from this book, Introduction to Chemical Engineering Simulation. So we will go to chapter number 12. Chapter number 12. Okay, separation column. This is chapter number 12. This is the plant. This is the first column. This is the de-methanizer column. There are 10 number of stages in de-methanizer. Okay. The second is de-ethanizer. there are 14 number of stages in de-ethanizer, and the third column is de-propanizer. There are 24 stages in de-propanizer. Okay. The feed now. The feed to de-methanizer, there are two feeds which are entering to the de-methanizer. So two feed, and the feed information are given. The material stream number 1, this is the material stream number 1 information, feed number 1, and this is the feed number 2 information. And the condenser and reboiler of de-methanizer is operating at a temperature and pressure value of. The condenser is operating at -125 degree Fahrenheit. The de-methanizer reboiler is operating at 80 degree Fahrenheit. The condenser pressure of the de-methanizer is 330 psi, and the reboiler pressure of de-methanizer is 335 psi. While the overhead molar flow rate is, suppose the overhead molar flow rate from de-methanizer is 133 kilomole per hour. There are 10 number of stages, and we will use the Finn-Robinson equation of state. To determine the condenser and reboiler duties of the de-methanizer. So now, after that, the feed from the de-methanizer will pump. So this is the bottom stream which is coming out from the bottom of de-methanizer will go to a pump, pass through a pump, and the pump will increase its pressure to 2790 kilopascal. So then you can see this is the feed will pass through a pump. So this is the pump, and then it will go to the de-ethanizer. This is de-ethanizer. Now the condition of de-ethanizer is given to us. This is a de-ethanizer column is a distillation column with 16 number of stages, 14 tray, and one is the reboiler and one is the condenser, and it operates at this pressure. The objective of the column is to produce a bottom product that has a ratio of ethane to propane. So the de-ethanizer will operate at this ratio. Propane to ethane to propane ratio will be 0.01. So this is the condition. This is the specification of the de-ethanizer. The name of the column, we can change the name. For example, we can rename it. So there are 14 number of stages. This is the feed stage is 16, the condenser partial. This is all the information of the de-ethanizer. Now after that, the feed will go to the de-ethanizer, then it will pass through the bottom of then the bottom of the de-ethanizer will go to a well to reduce its pressure. So this is the de-ethanizer information, and then it will pass through. Now we want this. We want the bottom of the de-ethanizer should contain 0.01% propane to ethane to propane ratio, and it will come out from the reboiler of the de-ethanizer, and it is on the mole fraction base and liquid ethane and propane. Then it will pass through. Then the stream from the bottom of the de-ethanizer will pass through a well. So this is the well. So a well. Then this a well is required to reduce the pressure of the bottom product of de-ethanizer, and it will, when it pass through a well, then it will then it will enter to the final column, which is the de-propanizer. So add well operation and product the following. So the well information is given. The feed, the inlet to the well is this one, and the outlet of the well is this one. We can write other we can rename these DC bottom, we can rename this. So we will rename these one, and this is the outlet pressure of the well should be 1690 kilopascal, which is equal to 245 psi A. So after that the feed will come to the de-propanizer column. So the information about the de-propanizer is also given. The de-propanizer column is represented as a distillation column which consists of 25 stages and 24 number of tray in the column plus one reboiler, and the total condenser is not counted as a stage. It operates at this temperature, this pressure. There are two process objective of the column. One is to produce overhead product that contain no more than 1.5 mole percent of isobutane and N-butane. And the second purpose of this column is that the concentration of propane in the bottom product should be less than 2%. So this is the distillation. This is the de-propanizer information. This is the information related to the de-propanizer. There are 24 number of stages. The condenser is total condenser. The condenser boiler pressure also given to us. The temperature, pressure, and specification value are also given to us. And we want the isobutane, N-butane, and the distillate. So isobutane and N-butane, we want isobutane and N-butane in the distillate, and it will come out from the condenser of the de-propanizer, and it will be, these component will be in the mole fraction and in the liquid form, and we will specify their value to 0.01, which is 1.5%. We will specify, we want 1.5% isobutane and N-butane, and the component are isobutane and butane, and the C3 in the reboiled liquid. So this is the C3 is the reboiled liquid stage, the reboiler fraction, and we want 2% propane in the bottom. So in the bottom, it shows that the concentration of propane in the bottom should be less than 2 mole percent. So it should be equal to or less than 2% propane in the bottom of the de-propanizer. So this is the information. What will be the condenser, reboiler duty, mole fraction of the component in the top and bottom, plot temperature and pressure profile, the mass and molar flow rate of all streams. So these are all the information, and these information are given in the book of Aspen HYSYS. First of all, we will add this external duty of the de-ethanizer is also given. So it show in the problem, it gives information that the external duty of the de-methanizer will be 2.1 multiplied by 10 raised to power 6 kilojoule per hour. So we will plot these, we will simulate this column in the Aspen HYSYS. So go to the Aspen HYSYS, open it, and click on new, double click on new. So this is a new simulation window is open. Now this is the component list. Add the component. So first of all, we will add the component, the stream of the de-methanizer. So the de-methanizer feed 1 and feed 2 information are given to us. So it consists of the nitrogen, carbon dioxide, methane, ethane, propane, isobutane, N-butane. So these are the component of feed number 1, and these are the component of feed number 2, and these are the temperature, pressure of feed 2. These are the temperature, pressure of feed number 1. So go to the, now click add the component of the column. So there are how much component? There are nitrogen, carbon dioxide, nitrogen, carbon dioxide, methane, ethane, propane, methane, ethane, propane, isobutane, click on this, add normal butane, isobutane, normal butane, isopentane, normal pentane, isopentane, add it, normal pentane, click on normal pentane, click on add, normal hexane, heptane, and octane, hexane, hexane, heptane, and octane, hexane, heptane, and octane. Okay, now these are components are added. Now go to the fluid package, and it shows in the problem that we should use the Finn-Robinson equation of state. Use Finn-Robinson equation of state. So click on the fluid package, click on add button, and add the Finn-Robinson equation of state, because the Finn-Robinson equation of state is mostly used for the hydrocarbons. For liquid water we can use the NRTL fluid package and some other fluid package, so we will use the Finn-Robinson equation of state. Now this green bar show that it is okay, this property package is okay. Now go to the simulation, click on simulation, okay, and add the material stream. So the period number 1, this is period number 1 of De-Methanizer, period number 2, okay, and this is the external duty of the De-Methanizer. Close this one. This is period number 1. Double click on it and give name to it. So we will rename it. This is the column 1 feed. Column 1 feed. Okay. The temperature feed number 1. The column 1 feed number 1. So C1 feed 1. Column 1 feed number 1. And its information is given. Its temperature is minus 95 degrees centigrade. Minus 95 degrees centigrade. Pressure is 2275 kilopascal, and the molar flow rate is 1620 kilogram mole per hour. 1620 kilogram mole per hour. Now it shows that unknown composition. So unknown composition of feed number 1. So put these composition. Nitrogen mole fraction is 0.0025. So 0.0025. Mole fraction is okay. Now carbon dioxide is 0.0048. And the other composition like so sum of mole fraction is equal to 1. Click on OK. So it is specified. Stream number 1 is specified. Now close this one, and it is specified. Now go to stream number 2. Double click on it and rename it. So column number 1, feed number 2. Specify the temperature, pressure. So the temperature is minus 85 degree centigrade. Minus 85 degree centigrade. The pressure is minus 85 degree centigrade. The pressure is 2290. 1290 kilopascal. Molar flow rate 215 kilomole per hour. 215 kilomole per hour. Go to the composition and add the composition. So nitrogen is 0.0057, mole fraction okay. And the remaining is 0.0027. So the sum of mole fraction is equal to 1. It is click on OK. So it is also specified. Now go to the this is the external duty. Double click on it and rename it X duty. The heat flow of the external duty is given to us in the question. 2.1 multiplied by 10 raised to the power 6. 2.1 multiplied by 10 raised to the power 6 kilojoule per hour. Okay. Close this one. Okay. It is okay. Power is 583.3 kilowatt. This duty. Now go to the methanizer. So click on the blue sheet. Go to the model and stream pellets and go to the separator. And here this de-methanizer is a reboiled absorber. So click on this one. Okay. Double click on it. Rename it column number 1. Okay. There are 10 number of stages. Okay. The inlet stage is period number 1. Column 1 period 1 is entering. The optional side stream, so it is the second stream is column 1 period 2, and the third stream is duty, external duty. Okay. Now the overhead from the column number 1 is column 1 top. This is the column 1 bottom. Now this is the condenser duty, and the reboiler condenser duty of column number 1. The reboiler duty of column 1. Click on next. Select once through reboiler. Click on next. And the top, the condenser pressure is given. So the condenser pressure is given. The condenser is operating at 330 psi and the reboiler is a little bit high pressure, which is 335 psi. So 330 psi. Top pressure is 330 psi. Okay, and the reboiler pressure is 335 psi. It is equal to 2310 Pascal. Okay, reboiler pressure drop, there is no information, so click on next. The top temperature and the condenser temperature and the reboiler temperature is given. The condenser is operating at minus 125 degree Fahrenheit, minus 125 degree Fahrenheit, which is equal to minus 87 degree centigrade. The reboiler is operating at 80 degree Fahrenheit. 80 degree. Okay. Click on next. So the boil off ratio. There is no information about the boil off ratio. There is no information. So click on done. Okay. Increase the size. And now click on run. So there is some error. So close this one. And now we will put some. Now we will go to the monitor. So here the degree of freedom is 0. Now the overhead product. So we will specify the overhead product. Well, the overhead molar flow rate is this one. Overhead molar flow rate is this one. So overhead product rate. So go to the click on add specification and column component flow. Click on this one. Click on add specification. The component flow. Okay, name is component flow. Okay, and the draw the stream. So it is from the top bottom of the column, from the top of the column. Molar base, it is okay. Specification value. So it is 1338 kilomole per hour. 1338 kilomole per hour. Okay, and component. Okay, so and these are the okay. Now this is a stream. Okay, now close this one and activate this one, deactivate this one. Click on run. So this is the component. So we will close this one. Overhead product rate. So we will component flow. So we will deactivate this one because we have information about the overhead product rate. So this is 1338 kilomole per hour. Okay, take this one. Okay, and it is converged. Click on run. So it is converged. Now close this one. This is stream number 1. This is the energy stream. Feed number 2. Duty. Feed number 1. Column. This is the top. This is the condenser duty, and this is the bottom. Okay, now the bottom of the de-methanizer will pass through a pump. It will pass through a pump. So we will add a pump. So go to the spinet and add pump. This pump, drag and drop pump. Okay, double click on pump. The inlet to the pump is the column number 1 bottom, C1 bottom, and the outlet is column number 2 feed, C2 feed. This will be the column number 2 feed. It shows the equal energy stream, so pump work. Okay, as you can see, energy. Okay, so energy, or you can rename it pump work. Delete this one. Pump work is okay. Close this one. Pump. Okay. Now the inlet to the pump, the pressure of the inlet, this stream is given to us. It is 2310 kilopascal, and the outlet pressure is, what should be the outlet pressure? It should be, click on this one, and the outlet pressure of the pump should be, it is given that the outlet pressure of the pump should be 2790 kilopascal, 2790 kilopascal, 2790 kilopascal. Okay, now it is converged. Now this speed will go to the de-ethanizer. So go to the separator, and the de-ethanizer is nothing but distillation column. Drag and drop distillation column. Okay, double click on column number 2. Column number 2. This is column number 2. Rename it. And how many stages there are? It shows that there are, in the de-ethanizer there will be 14 number of stages. 14 number of stages. 14 number of stages. The feed will inlet at stage number 6. So the inlet stream, the inlet feed will be the column number 2 feed. This is C2 feed, column 2 feed, and it will inlet at stage number 6. So actually this is okay, but this is in the problem. It should be at 6. Okay. Now, okay. Now the condenser type is partial, so this is partial is okay. And the overhead vapor product and the overhead liquid product, the bottom product, and the boiler duty, condenser duty, the condenser pressure, okay. Now this is the column number 2, so QC2, condenser duty of column number 2, and the boiler duty of column number 2, QR2. You can also put these DC2 condenser Q, but I am putting these value. You can put other value also. Now this is the vapor, so C2 vapor, column 2 vapor, column 2 top vapor, and this is the column 2 distillate. Okay, there is no side stream. Okay, now the bottom, so column 2 bottom, column 2 bottom, column 2 bottom. Then the numbering is from top to bottom. It is okay, in the previous column it was also from top to bottom. Okay, you can also from bottom to top. So click on next, and the revolver is once through the boiler. Okay, now the condenser pressure is given, value is given to us. The condenser pressure is 2725 kilopascal, 2725 kilopascal, 2725 kilopascal. Okay, the condenser pressure drop is 35 kilopascal. Condenser pressure drop is 35 kilopascal, 35 kilopascal. Reboiler pressure drop, there is no information. The reboiler pressure value is given. The reboiler pressure is 2792 kilopascal, 2792 kilopascal. And the column pressure, this column pressure should be between this one 2725 and 2792, which is about, it will operate between the condenser and reboiler pressure. So the reboiler pressure is 2792 and the condenser pressure is 2725. So it will operate between, and thus the value of the column pressure is this one 2760. Column operate at this pressure. Okay, the reboiler pressure drop information is, there is no information, so we will leave it. Now go to next, and the condenser and reboiler temperature. The condenser temperature is -4 degrees centigrade, -4 degrees centigrade. It is also optional, but in this problem it is given -4 degrees centigrade. Optional top stage temperature, so there is no information. The reboiler temperature is given 95 degrees centigrade, 95 degree centigrade, 95 degree centigrade, which is equal to 200 degree Fahrenheit. The overhead wafer flow rate value is given. So now we will click on next. The overhead wafer flow rate value is given kilomole per hour, and the value is given, it is 320 kilomole per hour, 320 kilomole per hour. The liquid rate, the distillate rate is 0. Distillate rate is 0. This is the distillate, it is 0. Okay, the reflux ratio, there is, I think there is no information about a reflux ratio of the column is, okay, it is 2.5 and it is on molar basis. 2.5 and it is on molar basis. Okay, this mass base, molar basis. Okay, now click on done, and now click on run. So it is converged, it is converged. Now we want what we want this specification in the de-ethanizer, the C2 over C3, the ethane to propane ratio of the D in the de-ethanizer should be 0.01. So it should be 0.01. So what we will do, it is already converged. You can see it is converged. It's converged. Yes, you two wafer. We'll delete this one. Okay. 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 Now double click on the column and we will add our own specification. So double click on the column, you can see it is already converged. So we will go to the monitor button in the design tab, and here the reflex ratio, this is okay, this is 320 is also okay, but we want the okay, but we want this ratio. So what we will do, we will deactivate one from these because the degree of freedom is 1. So I'm deactivating this one. Suppose I'm deactivating this one. So now it is unconverged and the degree of freedom is 1. So what we will do, we will add specification. It also working on this flow rate, but in the problem it shows that you should add these specification. So click on add specification, and because we want these percentage in the de-ethanizer, the natural gas plant, so we want these percentage. So go to the this is the column specification type. So the component fraction, the column recovery, the cutoff ratio, the column draw rate, okay, the column component recovery, column component ratio. Click on component ratio, column component ratio, click on add specification. So here the component ratio C2 to C3, C2 name is C2 divided by C3, ethane divided by propane, C2 divided by C3, name is this one, and the stage is a reboiler, so the stage is a reboiler, okay, click on reboiler. Flow basis is mole fraction, phase is liquid, okay, the specification value is 0.01, 1%, 0.01, and the numerator is this is the ethane, numerator is ethane, and the denominator is propane, ethane, and the denominator is, this is the numerator and this is the denominator. So this is the ethane and propane. Okay, now close this one, and now click on converge, click on run. So it is converged, you can see it is converged. Now close this one. Okay, now we will add the third column. So go to the flow sheet, go to the model and stream fillet, and go to the separator and add another distillation column for depropanizer. Drag and drop. Okay, double click on this one, and this is column number 3, which is nothing but depropanizer, column number 3, and the specific. Now okay, we will close this one. Now this is column number 3, but there is one thing between the column 2 and column 3. There is a wall, well, so we will put well to reduce the pressure of this bottom 2 stream, and we will enter the feed to this one. So we will add well, this is well, okay, well, double click on the well and rename it well. Okay, the inlet to the well is this one, column number 2 bottom. So column number 2 bottom, and the outlet is column number 3 feed. So C3 feed, and it shows the unknown delta P. So the outlet pressure of the well is given. This is the inlet feed and this is the outlet, column 3 feed, and this is the bottom of the distillation, column number 2. And the outlet feed, this outlet feed is 1690 kilopascal, 1690 kilopascal. 16. So go to the okay, so this one, click on this one. Pressure is 1690 kilopascal. Okay, it is converged. Well is also defined. Now we will click on the distillation column number 3, and this is the de-propanizer. Okay, the condenser is QC3, column number 3, condenser duty, and QR3 reboiler duty of column number 3, and at operate it is specification is okay. Now the third column, so it is a de-propanizer. It is a distillation column which consists of these number of trays. So the column 3 and the number of stages is 24. Number of stages is 24. There are 24 number of stages, one for this condenser. Okay, one for reboiler, and there is no condenser is not counting as a stage. So okay, the feed stream is entering at stage number 11. So the feed stream is entering. So this is the feed. This is the column number 3 feed. This is, select this one, and it is entering at stage number 11. Aspen HYSYS tell us that 12 is okay, but in the problem it shows that 11 is okay. So we will go to 11. Now okay, now the condenser type is total. This is the total condenser. Okay, there is no side stream. Okay, this is the overhead. So column number 3, top product, and this is the column number 3, bottom product. C3 bottom product. Okay, now we will click on next, and the reboiler is once through reboiler. Okay, the condenser pressure of column number 3 is, the condenser pressure is 1.5. The condenser and reboiler is operating at this pressure, and it shows that this column is operating as 1620. So this is a column is operating between reboiler and condenser pressure. Okay, condenser pressure is 1585 kilopascal. Condenser pressure drop is 35 kilopascal. The reboiler pressure drop, there is no information. The reboiler pressure is given. 1655 kilopascal. Okay, now okay, the condenser and reboiler duty or temperature are given. Okay, click on next. The condenser and reboiler temperature is given. The condenser temperature is 38 and the reboiler is 120. 38 degree centigrade, 38. It is optional, but in this question it is given, the value is given, so 120, 35 and 120. Okay, 38, condenser temperature is 38 and the reboiler is 120. 38, 120. Okay, click on next. Okay, the liquid rate. Okay, the distillate rate is 100 kilomole per hour and the reflux ratio is 1. The distillate rate is 100 kilomole per hour. 100 kilomole per hour. 100 kilomole per hour, and the reflux ratio is 1. What is the value? It is 1 on molar basis. So on molar basis it is 1. Okay, on molar basis. Okay, click on done, please. So okay, it is 1. Now click on run. So it is converged, it is also converged. So you can see the column number 3. This is the top, condenser, this is the top, the boiler, and this is the bottom. Okay, now but the information about in this problem is isobutane and n-butane we want. So there are two process objective of the column. One is to produce overhead product that contain no more than 1.5 mole % isobutane and n-butane, and the second, concentration of the propane in the bottom product should be less than 2%. Okay, so we will go to column number 3, double click on column number 3, and we will go to the specification monitor. So here these two are activated, so we will deactivate these two. Deactivate. Now click on add specification, and it shows that we want isobutane and n-butane and the distillate, and it should be 0.01, 1.5%. So isobutane and n-butane, isobutane and n-butane. So column, click on column component fraction, click on add specification, and it is from the distillate, the stage is distillate. Okay, it is the condenser, the component is isobutane and n-butane. C4 NC4, isobutane and n-butane, condenser. Okay, distillate, it is coming out from the condenser, so it is okay. Mole fraction and the liquid. So the liquid, it is in the liquid form, mole fraction and in the liquid form. Okay, specification value is 0.01, component isobutane and butane, so specification value 0.01, 0.01, and select the component isobutane and n-butane, isobutane, and the second component is also 0.01, 1.5%, and n-butane. Okay, if we click on this stream, so here you will click on this top and bottom, the top of column number 3. So I am selecting this top of column number 3. So suppose I am selecting stream, so I am selecting column 3 top, which is nothing but distillate. This distillate column, and distillate of column number 3 is okay. Column 3 top is the distillate, column 3 is the distillate. Okay, these values are specified. Now you can also click on stage, but this is, I will select the stream, close this one. Okay, now I will select the second information is we want the concentration of propane in the bottom product should be less than 2%. So 2%. Okay, I will click on add specification, click on column component fraction, click on this one, and here the column component fraction, and it is it is C3N reboiler liquid. So again it is stream, and the column name is, what is the name? The name is C3, which is propane. C3, the propane in the bottom should be, and the reboiler should be 2%. So the stage is a reboiler. Stage is a reboiler. So we will select the stage because it shows stage. Okay. The previous was also stage, so we will select the stage. Stage is a reboiler. Reboiler. Okay. Mole fraction is okay. Mole fraction, liquid phase, specification value 0.02. Liquid 0.02, and which component? This one, propane. So the propane. Okay. Now there was one, this, click on this one, and this is not top stage, but this is stage. So we will select on stage and condenser. We will stage, the stage is condenser. So condenser, click on OK, close this one, and now these two are specified. Click on run. So it is converged. It is converged. So it is converged. Now it is converged. Now the question is the condenser and reboiler duty for all column. So the condenser and reboiler duty. The condenser and reboiler duty. The condenser duty of this depropanizer is 1308 kilowatt. The reboiler duty of this column number 3 depropanizer is 1133 kilowatt. The condenser duty of the de-ethanizer is 3171 kilowatt. The reboiler duty of this is, second column is 3171. The condenser duty of column 2 is 1963 kilowatt. The condenser duty of the reboiler duty of this column is, the reboiler duty of the de-ethanizer is 2863 kilowatt, and this is the external duty which we have supplied, which is 2.1 multiplied 10 to the power 6 or 583 kilowatt. Okay. The second question is the mole fraction of all components in the bottom of all stream. So go to the top and see the composition. So column 1, in the column 1 top, these are the mole fraction of nitrogen, carbon dioxide. Okay, there are 96% methane is obtained in column number 1 top. Okay, and it is good for this plant. Column number 1 bottom, click on this one, go to the composition and check the composition. So here you will see 62% ethane and 26% propane. Okay, close this one, go to the top of column number 2 here and select the composition. So this consists of 92% ethane because it is de-ethanizer, so we want to produce large amount of ethanizer at the top of this column. Okay, this is the wafer. So go to the top wafer and find the composition. So in the top you can see this 96% ethane. Okay, go to the bottom, find the composition, click on composition, and here you will see in the bottom there are 66% propane, no nitrogen, no carbon dioxide, so there are 12% isobutane, and so okay. This is the de-ethanizer. So ethane is large amount of ethane is removed. This is the ethane, 6% ethane. Okay, large amount of ethane is removed. Okay, now go to the third column, and here select on this feed. You will also feed and find the composition. So here this is again 66. Okay, the oil just decrease the pressure. Go to the top of the propanizer, depropanizer, and large amount of propane. You will see large amount of propane, 98% propane, because it is a depropanizer. Go to the bottom and check. So this is 36%, and propane, you can see propane, it is about 2% propane. Okay, now the third question is plot the temperature, pressure profile, the mass and molar flow rate of all streams. So the mass flow rate, you can see the mass, the molar flow rate of this stream is 120.6 kilomole per hour. The molar flow rate of this stream is 5819 kilomole. You can also double click on this one and check the mass flow rate. So the mass flow rate is 5320 kilogram per hour. You can also check, suppose I am checking the mass, the molar flow rate of this one is very small, 4.9 multiplied 10 to the power minus 6 kilogram mole per hour, and the mass flow rate is 1.5 multiplied by 10 to the power minus 4 kilogram per hour. Okay, you can also check the molar flow rate is 178.8, and the mass flow rate is 9022 kilogram per hour. Okay, now plot, we can also plot like the temperature, pressure profile, etc. So for example, go to the first column, double click on it, go to the these are the manometer specification, this is the parameter. Okay, these are the pressure versus the tray position from top. So there are 10 number of trays, and here you can see the pressure. The pressure is, this is the pressure is increases. This is the pressure 23 10 23 5 23 00. So this is the pressure is increases as we go from stage number 0 to stage number okay, stage number 10. So the pressure is increases. You can also go click on estimate. These are the nitrogen, etc., other propane, ethane, propane, and these are the, go to the efficiency. The column efficiency is 11. You can also change, suppose you can also 95 and some other efficiency. Suppose I am changing it to 90% efficiency. Click and specify. So now the column efficiency is 90, but I don't want 91%. Click and specify. So 1% is okay. Now go to the solver. Okay, go to the side stream. Okay, the internal, you can add the internal like packing material, some others. This is a sieve tray, so you can also add some packing material, the sections, etc. The hydraulic profile of the column, you can also go to the rating. Okay, this is a sieve tray, and the column diameter is this one. This is the okay, the column diameter, and the column internal, the tray spacing is this one by default. Okay, go to the worksheet. These are the temperature, pressure, etc. Go to the performance, and here this is the flow sheet. Okay, this is the reaction. There is no reaction. The dynamic, you can see the height of the column is this one, 1.79. The diameter, the reboiler height diameter, you can see. Okay, go to the performance again, and go to the column profile, the temperature, pressure, etc. where you are given. Okay, the net feed is this one, the draw, the duty, this is the duty. the reboiler kilogram per hour, this one. The reboiler duty is this one. Okay. Okay, this is the condenser reboiler. You can also check the condenser. There is no information, there is no condenser in this column, so the reboiler duty is given. This is the reboiler duty and the output flow rate from the reboiler. So the internal plots. Okay, the column profile. Go to the plot. In the performance tab, go to the plot. You can plot the temperature, so you can also view the plot. For example, click on this one. This is the plot. Here you can see this is the temperature increases. You can see as we go from stage number 0 to stage number 10. Okay. The pressure, click on graph. This is the pressure. The pressure is also changes as we go from top to bottom. Okay. The flow profile, view graph, the flow. So here this is the green one, is this is the liquid, and this is the vapor, and their flow rate is changes as we go from top to bottom. The maximum flow rate, here you can see the liquid maximum flow rate is at stage number 8, and the minimum vapor flow rate is at stage number 5. You can see. Okay. The transport property, the K value, for example, K value, click on top. So this is the K value. The K value of nitrogen, carbon dioxide, methane. So here the K value of nitrogen at stage number 2.3 is 3.0 is about 12.48. Okay. You can also view the table. For example, view temperature. Click on table. This is the table. Okay. The top and the reboiler temperature is 19. So the temperature increases from this condenser to reboiler. Okay. Okay. Now close this one and go to the second. You can also view the same condition in the second and third column. For example, in the third column, double click on it, go to the performance, click on plot and click on the temperature profile. So here the temperature profile, here you can see the temperature is increases from top to bottom. The temperature of stage number 25 is 109 degrees centigrade. For example, the condenser duty is this one of depropanizer, and this is the reboiler duty. Okay, the temperature, pressure, etc. Okay, you can also worksheet, the flow sheet, the reaction, the dynamic. So this is the column, the reboiler diameter, the condenser diameter of column number 3 is this one, the height. Okay, worksheet. So this was all about that how can we plot various columns in the Aspen HYSYS. Thank you very much for your attention. If you are new to my channel, please like and subscribe for upcoming videos. Thank you very much.